Hello there. In this video we're going to illustrate another technique and a method of integration known as trigonometric substitution. So before knowing trig substitution, you have to be familiar with trigonometric functions in the identities, or some of the most common ones, that are associated to it. Namely, sine squared theta plus cosine squared theta is equal to 1, and 1 plus tangent squared theta is equal to secant squared theta are probably the two of the most commonly used ones. A couple others that you may want to be aware of, cosine squared, hyperbolic cosine squared minus hyperbolic sine squared is equal to 1, and 1 minus hyperbolic tangent squared theta is equal to hyperbolic secant squared theta. So these four identities can be used for using a method called trig substitution, which I'll illustrate here. So to illustrate this method, we're going to use the integral of 3x times the square root of x squared plus 5 dx. So just based on observation, you should be able to solve this integral with the methods we've already talked about, actually. You can use substitution, and we'll illustrate this and then compare our new method solution to this one and see if they're equal. So we can let u be equal to x squared plus 5. If we let u be equal to that, then that means du must be equal to 2x times dx. And if that's the case, then that means dx must be equal to du divided by 2x. So if that is true, that means this is going to be equal to the integral of 3x times the square root of u times dx, which is defined to be equal to du divided by 2x. So we see that x will cancel here. So this is just going to be equal to the integral of 3 square roots of u du. Rewriting square root as a power, this is just going to be the integral of 3u to the power 1/2 du, and then we can use the power rule to sort of simplify this expression. Oh, we also forgot our 2 that's hanging out there. Let's not forget him. So 3 halves, 3 halves. Alright, so adding 1 to our exponent, this is going to be 3 halves times u, so u to the 1/2 plus 1 is going to be u to the 3 halves. Then we're going to divide by 3 halves here, plus some arbitrary constant c, and then our 3 halves will cancel, and we're just going to be left with u to the 3 halves plus c. And then we're just going to replace our u that we defined before. So u was defined to be equal to x squared plus 5 raised to the 3 halves plus c. So that means the integral of 3x times the square root of x squared plus 5 dx is equal to this function. Now we're going to do this approach in a similar way to sort of see that you can do the same integral in different methods and actually get the same exact solution. So we're going to consider the same exact function, 3x square roots of x squared plus 5 dx, and now we're going to use trig substitution. So the first observation that we need to make is that this radicand is of the form something plus x squared. So 1 plus x squared is going to be tangent squared, so we may be able to transform this radicand into something of that type. So we're going to let u, or x, be equal to the square root of 5 times the tangent of theta. Now usually we let something be equal to a function of x. Now we're letting x be equal to a function of a new variable. So trig substitution sort of works in a little backwards fashion than u substitution does. So if x is equal to this function, that means x squared is just going to be equal to 5 times the tangent squared of theta. Also, if x is defined to be equal to that, that means dx is just going to be equal to the square root of 5 times the secant square root of theta d theta. So we also don't have to solve for dx in this differential equation. Alright, so let us transform this integral using these new substitutions here. So this is going to be equal to the integral of 3x, so x is the square root of 5 times the tangent of theta, times the square root of x squared, which is 5 tangent squared theta, plus 5, times dx, which is the square root of 5 times the secant square root of theta, d theta. And we can clean this up just a tad bit. So we have square root of 5 times the square root of 5, that's just going to be 5, and 5 times 3 is just going to be equal to 15. So this is going to be 15 times the integral of tangent of theta times the square root, and I'm going to factor out a 5 out of this, so 5 times tangent square root of theta plus 1 times secant square root of theta d theta. So remember, we can factor out this square root of 5 outside of this primary square root, And then we're going to be left with 1 plus tangent squared, which is secant squared, and the square root of the secant squared will cancel. So this is just going to be equal to 15 square root of 5 times the integral of the tangent of theta times secant of theta times secant square root of theta d theta. I'm going to rewrite all of these functions in terms of sines and cosines only. So I have 15 square root of 5 times the integral of sine of theta divided by cosine of theta times 1 divided by cosine of theta times 1 divided by cosine squared of theta d theta. Combining everything, we have 4 cosines on the bottom, so we have 15 square root of 5 times the integral of sine of theta divided by cosine of theta all raised to the 4th d theta. From here I'm going to proceed with standard substitution. So we're going to let u be equal to the cosine of theta because his derivative is located on the opposite side. So du is going to be equal to the negative sine of theta d theta. So that means d theta is going to be equal to du divided by negative sine of theta. So transforming, this is going to be equal to 15 square roots of 5 times the integral of sine of theta divided by u was defined to be equal to cosine theta. So we have u to the 4th times d theta we found to be equal to du all over minus sine theta. By design, we have our negative signs that cancel, and we can factor out this negative sign out here. So this is just going to be equal to 15 negative square root of 5 times the integral of u to the minus 4th du. And now we can proceed with the power rule. So this is going to be negative 15 square root of 5 times, add 1 to negative 4 gives us negative 3, so u to the minus 3 divided by our new exponent, plus some arbitrary constant c. From here we can divide negative 15 by negative 3 to get a positive 5. So this is just going to be equal to 5 square root of 5 times u to the minus 3 plus c. Alright, remember what u was set to be equal to? U was set to be equal to cosine of theta. So we can just replace that to get a function of theta. So this is going to be equal to 5 square root of 5 times cosine of theta all raised to the minus 3 plus c. Now we need to go back in terms of x from theta. And this is where the trig substitution has its little, to some people, an uncomfortability. So remember, we let x be equal to the square root of 5 times the tangent of theta. So if that is true, then that means theta must be equal to the arctangent of x divided by the square root of 5. So if that is the case, then that means I can rewrite this as 5 square roots of 5 times the cosine of theta, and theta is equal to the arctangent of x divided by the square root of 5, all raised to the minus 3 plus c. Now this answer is definitely not equal to the other one we have, but notice that we have a function and a inverse function that pretty much behave similarly to one another. So a trig function and an inverse trig function. So maybe it's possible that we can cancel these out. So from this first identity, I'm just going to solve for tangent of theta here to get an observation. So tangent theta is equal to x divided by the square root of 5. And I'm going to use this fact to sort of figure out another way of saying the cosine of theta. So remember, we can make a right triangle since these are all circular trig functions, and I'm going to call this theta. So remember, tangent of theta is equal to the x divided by the square root of 5. And tangent theta in a right triangle is always equal to the opposite over adjacent for a right triangle. So I can call x to be equal to the opposite side and square root of 5 to be the adjacent side, since that's going to be true for any proportional triangle. So I'm going to call this x, and I'm going to call this the square root of 5. So I need to figure out what r is in this picture. So by Pythagorean theorem, we have that r squared must be equal to the square root of 5 squared plus x squared. So then we can find that r is equal to just the square root of the x squared plus 5. So remember what we want to find. So again, our integral is 5 times the square root of 5 times the cosine of theta all raised to the minus 3 plus c. So we need to know what the cosine of theta is equal to. So remember what cosine of theta is. So cosine of theta is always equal to the adjacent side over the hypotenuse of the same exact triangle. So the adjacent side of theta is going to be equal to the square root of 5, and the hypotenuse is going to be r, which is going to be the square root of x squared plus 5. So that is what cosine of theta is equal to. So this is going to be equal to 5 times the square root of 5 times the cosine of theta, which is equal to the square root of 5 divided by the square root of x squared plus 5, all raised to the minus 3 plus c. And now at least we've got rid of our circular trig functions, right? So let's proceed in algebraically manipulating this. So I'm going to flip my fraction with this negative exponent and turn it to a positive one. So this is going to be 5 times the square root of 5 times the square root of x squared plus 5, all divided by the square root of 5, all raised to the positive 3 plus c. And I'm going to express my square root in terms of a exponent. So that's going to be 5 square root of 5 times x squared plus 5, all raised to the 1/2. And that's actually going to be a 3/2 since it's going to be cubed. And the bottom is just going to be square root of 5 times the square root of 5 times the square root of 5, since it's square root of 5 cubed. So notice that the square root of 5 is going to cancel with that. And also square root of 5 times the square root of 5 is 5, which also cancels with that as well. So here we are. So this is going to be equal to x squared plus 5, all raised to the 3/2 plus c. So that means the integral of 3x times the square root of x squared plus 5 dx is equal to x squared plus 5 to the 3/2 plus c. And notice that we got the same exact answer regardless of the approach we did, but sometimes you won't actually have an option of the method you should use, whether you should use substitution, partial fraction decomposition, completing the square, and so on. But this is one example of how to use trig substitution. So there's just a couple unique things that are associated to trig substitution. Namely, we let x be equal to some function of theta. In this case, we chose square root of 5 times the tangent of theta. And also another unique thing that is associated with this is where you have to use the right triangle to sort of cancel out the trig functions. So remember, we had to use like a right triangle to sort of rewrite that cosine of the arc tangent of x divided by the square root of 5 expression. So that's another thing that is also unique to the trig substitution approach. But in the next video, we'll use a trig substitution again to solve another integral as an example.